to your 9th and 10th lesson. We're going to finish up Chapter 1 with these two lessons. So, our first lesson that we're going to be doing is estimating roots. That should be a fairly quick lesson because you guys already did square roots and cube roots. Now we're just going to be estimating. And then the next lesson that we're going to be doing is comparing mathematical expressions, which means that we're just going to take what we know about roots and numbers, and we're going to compare them by saying this one is bigger than this one, and so forth. So these are the two lessons that we're going to be working on. Make sure you copy this down. Let's get started on your vocab, and then see you in the lesson. Alright, for our vocab, we got two vocab words today. We have irrational number. That's just a number that can be expressed as a fraction. And the second vocab word that we have today is irrational number. Irrational number is all real numbers, which are rational and irrational. There will be numbers that you'll learn later on in mathematics called imaginary numbers. So, all real numbers, which means natural numbers, whole numbers, integers, and rational numbers are real numbers, as well as irrational numbers are also real numbers. So, those are our two vocab words for today. Let's go ahead and start lesson 9 and then move right into lesson 10. Alright, for our first example, we're going to be estimating the square root of 83 to the nearest integer. What I did here was I actually wrote down all of the perfect squares that I know, all the way up to 12. Square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 4, and so forth, all the way down until I got to 12. So if you have this, which you guys should have had it from the previous lesson, this is what I really have. This is why I said it's kind of important to know your perfect squares. So what we're going to do is we're going to estimate where the square root of 83 is going to be. So I'm going to look at 83. And I'm going to look at my perfect squares, and I'm going to say, where's 83 closest to? Because it asked me to estimate to the nearest integer. Well, I have 81 as the square root of 9, and I have 83 is close to 81, so that must mean that the square root of 83 is about 9. Now, I'm actually going to type it in my calculator to see what the square root of 83 is. Square root of 83? 9.11. So the square root of 83 is actually 9.1104335579. Well, that's a really long decimal, and so what we do sometimes is we actually round the square roots to their whole numbers. Now notice I use these to kind of estimate where it should be around. Whichever one it's closest to, that's where I would be rounding the integer to. And integers are numbers that are whole numbers, but then they're opposites. So like positive 1, positive 2, positive 3, negative 1, negative 2, negative 3. So again, the square root of 83, the closest integer to it is 9. You can say positive 9, or you can say negative 9, because both the positive and negative number will equal 83 if we square them. Alright, in our next example, example number 2, we're going to be finding the square root of 54 to the nearest integer, just like we did. So again, I'm going to look at 54, I'm going to look at my perfect squares, or think about my perfect squares if I don't have the list, and say, where would 54 be closest to, or what two integers would 54 be in between? Well, I know that the square root of 49 is 7. So this is 7. And I know that the square root of 64 is 8. And 54 would be somewhere in between there. So now I'm going to say, where is 54 going to be closer to? Is it going to be closer to 49 or 64? Well, 54 plus 10 brings me to 64. And 49 plus 5 brings me to 54. So this is only 5 away, where this is 10 away. So 54 is closest to the integer of 7. So I'm going to say that the square root of 54 is about 7. You could say plus or minus 7, or you could just say just 7. 7's fine too. I'm going to check it. Square root 54 is 7.3. Yes, that's even more closer to 7 than it is to 8. So hopefully you're kind of getting this. All we are is rounding and figuring out what two ones it would be between, and then using those to figure out if we're going to round that number up or down. Alright, to do question number 3, you might want to copy down your perfect cubes now. So this means some number to the third power is going to equal the number that's inside the radical sign. So the third root of 1 is 1. The third root of 8 is 2. The third root of 27 is 3. Third root of 64. So this is all the way down to 10. So make sure you have those. What we're going to use is we're going to use these integers to estimate where this number is. So this question says, where's the cube root, or the third root, of 320? So I'm going to look at this and say, where would 320 be between what two numbers? Well, I see that 216, the cube root of 216 is equal to 6, and the cube root of 343 is equal to 7. So I know that this number is between these two. Well, the next question is, which one is it closer to? Well, 320 is actually closer to 343, so I'm going to say that the cube root of 320 is about 7. And that would be my answer to this problem. The reason why we pick 7 is because we see that it's only 23 away here, where here it's almost 100 away. If this had 4 more, it would be 100 away. So we're 96 places away. 96 is a lot further than 23. So that's what we're doing. Good to go on that. Let's try one more like this and then keep moving. In example 4, what we're going to be doing is we're going to be doing exactly what we did in example 3. We're going to estimate a cube root. So we're not looking at the perfect square chart. We're looking at the perfect cube chart, and we're going to decide where is 100 closer to. Well, 100, if I'm following down here, is somewhere in this area right here. So it's between 4 and 5. So I know that the square root of 64 would be 4, and I know that the square root of 125 would be 5. So my question is, which one is it closer to, 64 or 125? Hopefully you're thinking 125. So this cube root, and I should put a cube in these, the cube root of 100 is about equal to the number 5. If you actually type it in your calculator, you're going to get 4.6. And 4.6, that 6 is above 5, which means we normally round up anyways. So it's closer to the number 5 than it is to the number 4. So if you're graphing on the number line, you put it just a little bit above 4.5. And that's really it for this part. Let's keep moving. Alright, are you on to our last example for lesson 9? Then we're going to switch into 10. In example 5, what we're going to be doing is estimating by using a formula. So we're going to use the estimation ideas that we thought about earlier to solve this problem. So it says to estimate the time in seconds it will take for an object to fall h feet, you can use the expression the square root of h divided by 4. About how long will it take for an object to fall from a height of 38 feet? So we're assuming that h is how high up the object is, and so we're going to plug in 38 for h to figure out about how long it would take to fall. So the first thing we want to do is figure out what is the square root of 38 about. So we can estimate this to figure out about how long it would take for that to hit the ground. Well, the square root of 38 is between the square root of 36 and 49. It's actually closer to 36, and the square root of 36 is 6. So what I would be doing is I'd be taking 6 and dividing it by 4 to figure out about how long it would take for that to hit the ground. Well, if I change this to a mixed number, I'd get 1 and 2/4, and 2/4 is actually 1 1/2. So in order for the object to fall and hit the ground, it would take me about 1 1/2 seconds. That's it for this lesson. We're going to move on to the next lesson in the same video. It should go quick as well, because all it is about comparing, telling me which one's bigger, which one's smaller, and going from there. In our next lesson, one of the first things we're going to be doing is we're going to be classifying numbers based on what category they fall into. So there's 4 main categories that you're going to be using. You have natural numbers, whole numbers, integers, and rational numbers. There is a 5th category, but that one is kind of a little bit different. The last category is irrational number. It's a number that cannot be written as a fraction. So pretty much anything that you can't classify as one of these it's classified as irrational. Now let's talk about the top 4 though. A natural number. A natural number is counting numbers. Like when your parents teach you how to count, they're like 1, 2, 3, 4. So they start at 1 and they count up, and they're all positive numbers. So natural numbers start at 1 and count up. Whole numbers. Whole numbers are exactly the same as a natural number, but a whole number includes 0. So what that means is if I have a number that's classified as natural, then it's also a whole number. But a whole number, if it's 0, is not a natural number. We don't naturally count 0 when we're counting. So whole numbers start at 0 and they count up. So 0, 1, 2, 3, 4, and it keeps going on forever. Integers are whole numbers and they're opposites. So an integer starts at 0, it counts up, but it also counts down. 0, -1, -2, -3, it's the opposite of a whole number. So the opposite of a whole number, the opposite of positive, negative. So again, right now you haven't talked about decimals, you haven't talked about fractions. Integers are whole numbers and they're opposites. So if you can classify a number as an integer, then it has to be kind of classified as rational number as well, because a rational number are decimals, integers, and fractions, like -3, 5, 5/8, and 14.2. So a rational number is really any number you can write as a fraction. If you can write it as a fraction, that's rational. So here's how it works. If you can classify a number as natural, then that means it's also whole, it's an integer, and it's a rational number, because it falls into all 4 categories. A natural number is a counting number. It could start at 0 and count up. It's also an integer because it's exactly the same as a whole number. And it's a rational number because I can make any counting number a fraction by putting it over 1. A whole number, if it's 0, is not natural. So most whole numbers are natural numbers. The only one that's not is 0. If you can classify something as a whole number, and that's the only category you can classify it as, then it's also an integer, and it's also a rational number. 0 is a rational number. You can put any number, 0 divided by any number will make that a fraction. 0 divided by 1, still 0. Integers, if you're talking about negative numbers, then the only thing a negative number would be classified as is a rational number. If you're talking about 0, 1, 2, well then you already classified it as whole, you already classified it as natural. So it only falls in, if you have an integer, and that's the only classification that you can think about because it has negative numbers, if you have an integer, you can also classify it as a rational number. And then if you have a decimal, you can classify it as rational numbers as long as that decimal can be written as a fraction. If you can't figure out how to write that decimal as a fraction, like it continue on forever, like pi, then that's irrational. So what we're going to do is we're going to look at some problems and we're going to see if we can classify them based on the definitions we have here. And don't worry if you don't remember these. I got a nice little song for you guys to listen to about these. Alright, so you guys just wrote the classifications of numbers. We're actually going to apply that to see if we can classify this number into which part of the real number system it belongs into. So for our first example, it says name all of the sets of numbers to which the real number belongs into. So let's think about it. Is this number that we see right there a natural number? Does it seem like it's a counting number? Do we start at 1 and say 1, 0.25252525? No. So that's not a natural number. Your parents didn't teach you how to count by decimals. Whole number. Well, if it's not natural, then it's not a whole number. Because in order for it to be a whole number, it had to be 0, 1, 2, 3, 4. They didn't go 0, 0.25, 0.252525. So it's not a whole number either. So right now, this would not be classified as natural or whole. That's not an integer because it's not a whole number, and it's opposite because that's not a whole number. Is that a rational number? Can I write that decimal as a fraction? Well, that's a repeating decimal, and we learned in lesson 1 that we can take any repeating decimal and write it as a fraction by putting it over 9, 99, 999, 9,999. It just depends about how many numbers are repeating. So in this case, we could write this as a fraction as 25 over 99. Since we can write that as a fraction, this is a rational number. It does not fall into integer, whole number, or natural. So this means that it's a rational number. We could write it as a fraction. So the only classification for this one is a rational number. It is not irrational because irrational means we can't write it as a fraction. We've already wrote it as a fraction. So the one classification or the number set that this falls into, rational number. Let's try example 2, working on another one that has a decimal. So if it has a decimal, it's not natural, it's not whole, it's not integer, so it's between rational and irrational. So all I gotta ask myself is, can I write this as a fraction? 0.090909. So since it's a repeating number, I can write it as a fraction. There's only one number that's repeating. It's 9 over. Since there's actually two spaces though, there's actually two numbers repeating, sorry. So there's two numbers repeating. It's a 0 and a 9, but I only need to write the number 9. So it's 9 over 99. If I wanted to, I could put 09 over 99, but again, you don't need that 0. So the fraction would be 9 over 99. Well, that equals 1/11th if you simplify. Since you can write it as a fraction, we're going to call it rational. It's a rational number because we can write it as a fraction. And that's all we got to do for this type of problem. I'm going to give you some more to practice. So we're actually going to get quite a few examples just to make sure we can tell where they belong. And that's what we're going to do. All right, so I decided to give you the whole number 5. Our job is to figure out where does 5 belong. Well, when our parents teach us how to count, they teach us 1, 2, 3, 4, 5. So 5 is a natural number, so I'm going to write N for natural. If it's a natural number, then it's also a whole number because whole starts at 0. It counts up 1, 2, 3, 4, 5. So 5 would also be a whole number. 5 is also an integer. Would I normally see 5 on a number line? Yeah, and it's also a whole number, so it's an integer. And 5 is also a rational number because I could write it as a fraction. 5 over 1 is still 5. So since I could write 5 as a fraction, I know it's rational. Since it's a number I normally count, that's natural. And if it's natural, it automatically has to be whole. And if it's whole, it automatically has to be an integer. So what happens is, if you can classify it as natural right off the beginning, it's no matter what going to be whole, integer, and rational. If you can classify it as whole, and that's the only thing you can classify it as, then it's also integer and rational. Let's see what we can do. So here's the same question, -2 this time. Well, -2 is not a natural number. We don't count up to it. And it's not 0, 1, 2 to get to -2. So it's not whole. But -2 is normally on a number line, and it's the opposite of a whole number. The whole number being 2, it's the opposite of 2, it's -2. So -2 would be classified as an integer. And if I can classify it as an integer, then I'm also going to classify it as a rational number. I could write -2 as a fraction by putting it over 1. So the two categories that -2 would fall into is integer and rational number. All right, so number 5, example 5, -15.5. It's not a natural number. We normally don't count by 0.5s. It's not a whole number because it doesn't fall on a number line in the positive direction. It's not an integer because, again, normally we don't put it on a number line. It's not the opposite of a whole number. But it is rational because I could make it a fraction. This is -15 and 5/10, and if I had to make this a fraction, I could make it an improper fraction by taking 15 times 10 and adding 5, so I'd have a -155 over 10. So I was able to make that a fraction. Since I could make that a fraction, that means it's a rational number. So most likely, if it's a decimal, it's rational if your decimal ends or your decimal repeats. If your decimal does not end, does not repeat, chances are it could be irrational. Alright, so example 6, I put square root of 2 on the board. I'm actually going to type in my calculator to see what the square root of 2 is. My calculator says the square root of 2 is 1.414213562, and my calculator stopped, but I believe that this decimal keeps going on and on and on. So since this decimal does not stop, it's not rational, because I cannot write the square root of 2 as a fraction that's actually going to work very well. So in this case, it's going to be irrational. This would be an irrational number. So in this lesson, one of the first things we're doing is we're classifying numbers into what number set they belong based on the rules. And again, don't worry, I got that nice lovely song for you guys to listen to on Tuesday to kind of help bring it home. I want to give one last example that we're going to look at. It's the square root of 36. Well, the square root of 36 is actually equal to 6. So if we know the square root of 36 and we're trying to classify it as one of these, we need to actually change it to its number so that way we can figure out what number it belongs into. In this case, 6 is a natural number because we count it. Well, if it's natural, then it would be all the other categories of whole, integer, and rational. It would not be irrational because I can write 6 as a fraction, 6 over 1. Now, you cannot write a square root as a fraction by putting it over 1, but you can write a whole number as a fraction by putting it over 1. Since this number could be expressed as a fraction, then that's why we're going to call it rational. So 6 is a number we normally count. 6 starts at 0 and does count up. And 6 is also on a number line. 6 could be written as a fraction. That means it falls in 4 categories. So if you are able to change a square root to an actual number and that number stops, the number does not keep going, then we can classify it as one of these categories up in the top. If it keeps going and it doesn't repeat, then it's probably going to be irrational. Alright, so when doing the next example, what we want to do is we want to read the question and then decide how we're going to approach the problem. So here it says fill in the circle with less than, that's what it means. It means that one number is less than, greater than, or equal to make the statement true. So to make a true statement, we have to fill in that circle with either less than, greater than, or equal to say what's happening between these two numbers. So one of the first things that I suggest, this is up to you, but I suggest that you change everything to decimals. It's a lot easier to compare decimals and to look at those and say which one is bigger than the other. So what I'm going to do is I'm going to type the square root of 7 in my calculator. Square root of 7. That's 2.6457. It keeps going, but I'm going to write down that many decimals. And 2 to 2/3, so I'm going to figure out what 2/3 is. Well, this is 2, because that's what the whole number is. That's always in front of the decimal. And 2/3 is 0.6666, and the 6's go on forever. So in this case, we got to figure out which one's bigger. 2.64 or 2.66. And if you're listening to how I just said that, then I can tell you which one's bigger. What we do is we look at what matches. 2 matches, 6 matches. Look at that. That's a 4, that's a 6. Since this one has a 6, 6 is bigger than 4, that means that this is less than that. And since we say it's less than, we point at the smaller number. And what I mean by point, it's like an arrow. If you were to draw a line through this, that means you're pointing at the smaller number. So whenever you're doing the less than or greater than sign, kind of make it like an arrow and point at the smaller number. Another thing that some people say is that Pac-Man eats the bigger number. So if you were to kind of erase some of the circle, now it looks like Pac-Man. And Pac-Man's going to eat the bigger number. This number is bigger than that number. Let's do a couple more of these. Alright, example 9. We're going to be comparing the square root of 15 to 3 7/8. So again, I'm going to change the square root of 15 to a decimal. Well, the square root of 15 is 3.8729. And 3 is going to drop down. So 3 comes down. And I'm going to figure out what 7 divided by 8 is. Well, 7 divided by 8 is 8 0.875 or 0.875. So now looking at these two decimals, I should be able to tell which one's bigger. 3, those match, so keep going. 8, those match. 7, 7. This is 2, this is 5. 5 is bigger than 2. So again, that means that the square root of 15 is less than 3 7/8. And that's how we approach these problems. We want to change them to decimals and then compare them. But always leave your answer in the original format, so that way you can tell which one's bigger or smaller. Your work is when you're showing me that you changed them to decimals, so that way you could tell me where they're different. In example 10, still working on the same type of situation where we're comparing two numbers. This time we have a percent and we have a radical or a square root. So what we have to do is, again, change them to decimals. All percents can be divided by 100. So this is 15.7%. Well, I could type 15.7 and divide by 100 to get my decimal. So I'm going to type that in my calculator. 15.7 divided by 100, because all percents are over 100, and I get 0.157. Now I'm going to type this in my calculator, the square root of 0.02. And when I type that in my calculator, I get 0.1414. And it kind of keeps going, but I could stop there because I can tell that they're different. So now I just got to say which one's bigger. Well, I have 1, I have 1, I have 5, I have 4. 5 is bigger than 4. So again, I like to say Pac-Man eats a bigger number. So this is my bigger number, so that's where the mouth is going to open up to. 15.7% is bigger than the square root of 0.02. Continuing on. So we were able to tell which was bigger between two numbers. Now we're going to have to tell which is bigger between four numbers. So we have a square root, we have a whole number, we have a mixed number, and we have a decimal. And we have to now be able to tell which is bigger between all of these. One of the key things that I recommend that you do is you change them all to the same format. So if you already got decimals, change them to decimals. So what I'm going to do is I'm going to change each one individually, and then later on, at the very end, I'm going to change them back, so that way they're all written on the number line based on from least to greatest, because that's what the directions tell me. So first thing I'm going to do is I'm going to figure out what the square root of 30 is, and I'm going to write down its decimal. The square root of 30 says 5.477, and I could probably stop there. 6 is already written as a number, so 6 is equal to 6. 5 and 4/5, so 5 and 4/5 is going to be, well, the whole number is 5, so 5.4 divided by 5 is 8. So this is 5.8, and this is already written as a decimal. So what I have is I've changed them all to decimals. 5.477, 6 is it's already a decimal, 5.8, and 5.36. And now we have to order them from smallest to greatest by verifying them on a number line. So what I'm going to do is I'm going to draw a number line. I'm going to put 5 on this side. This is 5.25, 5.5. This is 5 3/4, and this would be 6. So what I did was I marked based on quarters. This is 5 1/4. This would be 5 3/4. Because I separated this into 1, 2, 3, 4 pieces. So there's 4 different spots on my number line. Now, all we gotta do is plot these numbers somewhere about where we believe they should be. Well, I know the square root of 30 is 5.477. 4/7 is probably really close to 1/2. So I'm going to put a dot right by my 1/2, and I'm going to call this the square root of 30. So the square root of 30 is close to 5.5, but it's not actually 5.5, so I put it really close to 5.5. This one is at 6, so I'm going to go ahead and put a solid dot at 6, and I'm going to say that that's where 6 goes. So I'm going to write the number 6. This is 5.8. Well, I know that 5 3/4 is 5.75, so 5.8 would be just a little bit in front of it. So I'm going to call this 5 and 4/5. Now notice when I'm writing the numbers back on the number line, I'm putting them back in their original form. And now the last one, 5.36. Okay, well this is 5.25, this is 5.5, 5.36 would be just a little bit, maybe more like in the middle between these. So I'm going to write that this is where 5.36 repeating 6 goes. So what I did was I ordered my numbers from smallest to largest on the number line. So my answer is 5.36, comma, square root of 30, comma, 5 and 4/5, and then finally 6. And what I did was I verified by seeing those numbers on the number line based on their decimals. So I know that my answer is right, because if we think about a number line, this came first, second, third, fourth. So least to biggest. Alright, so for our last example, great job for making it this far. I know this is probably about 30 minutes, maybe 40 minutes. Not what you guys want. Whatever. For our last example we're going to be doing is we're going to be solving one more problem just like our previous one, just to kind of make sure that we got it for sure before we actually call it good. So we have the square root of 15, we have 3, 4.5, and 4.21, and that 2 ones repeating as bar notation. Now we got to put it in order from least to greatest on a number line. So before we do that, let's change them all to decimals like we did before. So I'm grabbing my calculator. The square root of 15. The square root of 15 is equal to 3.872. 3 is already a number. 4.5 is 4.5, I know that. And 4.21, repeating, looks like that. So looking at these, I might actually be able to tell which one's bigger and smaller, but I still need to follow the directions. It says that I need to put them on a number line to be able to tell the difference between which one's bigger and smaller. So start with the number line. I'm going to start with the number 3. Then I'm going to put 3.25, 3.5, 3.75, 4, 4.25, and 4.5. So I counted by decimals of 0.25 as I made my number line. You can count by whatever you want as long as you put them in the correct places. So first number I'm going to put is the square root of 15, which is 3.872. 872 is close to 3.9. 3.9 would be close to 4. So I'm going to say that this right here is where my square root of 15 goes. My next number is 3. Well, 3 is already marked, so this is where 3 goes. Next number is 4.5. Well, that's already marked, so 4.5. Oh, sorry, it's not 4.5, it's 4.5. So all I have to do is write that this is 4.5. And then 4.21, well, this is 4.25, so 21 would be very, 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 very close. And it's going to be right there. So now I just say, well, my order goes from 3, square root of 15, 4.21 repeating, and 4.5. And that would be my final answer. You guys did awesome today. Make sure you like this video, smash that notification bell if you haven't hit that, to make sure that you can get any notifications when I post these videos. And I'll see you guys on Tuesday.